Okay, so this example, which is 3140, is taken from the Gelmarium book, and this is one of the example in your tutorial sheet. So the 4 kilogram slider is released from rest at A and slides with negligible friction down the circular rod. So this is location A, and it's moving in this direction here, and the way the mass is 4 kilogram, and the friction is negligible, so there will be no friction force. Determine the velocity of the slider as it reaches the bottom at B. So you need to calculate the velocity here, and then the maximum deformation of the x of the spring. So you also need to calculate the maximum deformation of the spring. So the given data here is what we are given is M, which is 4 kilogram, and is released from rest at A. So this means that the velocity at A is 0 meter per second, with negligible friction down the circular rod in a vertical plane. So this means that the friction is negligible, so the friction force will be 0. And you need to determine the velocity v of the slider as it reached the bottom at B. So you need to calculate the velocity at position B when it will just touch the spring here, and then you need to calculate the maximum deformation of the spring. So you need to calculate the x in the spring here. Okay, so this is the problem that we need to solve. So this is our part A, and this is our part B. So in part A, which is obviously from A to B. So when this slider moved from A to B here, and it is just touch the spring here. So again, we can solve this using the work and energy equation. So what we can write is the work and energy equation between location A and location B. So what we will write, the first location is A, so we will write kinetic energy at A plus potential energy at A plus work done by all the forces other than gravity and springs, and equal to the final potential energy, which is TB, and then the final potential energy, which is VB. So T is the kinetic energy and V is the potential energy here. Okay, so now as you can see, if you take this as our datum point with h equal to 0 here, so then we can say that the h here is given, which is this this distance here, 0.6, which is the radius of this this arc here, so which is 0.6 from here to here, which is this 0.6 here. So the height at A is given, which is mgh, and we know that the initial velocity at A is 0. So we know that the if the velocity is 0, so then the kinetic energy is 0, which is half mv square. And then what we can write is that the total potential energy will be equal to potential energy of two parts. So one will be the potential energy VGA, and then it will be VEA, and similarly this will be split into two parts, so VGB, and this will be VEB. So the Vg is the gravitational potential energy, and Ve is the elastic potential energy. Similarly, this Vb is the gravitational potential energy at location B, and the elastic potential energy at location B. So as you can see in this specific case, in location A there is no spring, so obviously this uh, elastic potential energy will go to zero. The only potential energy that we should have at location A is VGA, which is just mgh A, and in this case, because there is no other force than gravity and friction, gravity and spring, so this means that this term will also goes to zero. Now on the right hand side, what we have is the body is now obviously moving with some velocity, so we will have some kinetic energy here. So half mvb square, which is half times mass times velocity square. And if you look at location B here, so obviously height is zero, so then the gravitational potential energy is zero at location B, and we have a spring here, but at location B the spring is just touching the mass is just touching the spring, so there is no deformation in the spring, so there will be no force in the spring, so there is no elastic potential energy in the spring, so this will be zero. And here you can write the reason that mass is just touching the spring, so x is equal to zero, so there is no deformation in the spring. So if there's no deformation in the spring, so the elastic potential energy will be zero. So we just end up with this equation here. Now in this equation, even you can cancel m on both sides. So you are given g here, which is 9.81. HA is given, which is 0.6, and on the right hand side you have half VB square. So from here you can easily calculate VB, which will become equal to 3.43 meter per second. Okay, now the part B is that we need to calculate x of the spring. So this means that when the slider will arrive at location B, it will not stop here because it's still moving with some velocity, so it will try to compress the spring. So we need to calculate the maximum compression in this spring here. So to calculate that maximum compression in the spring, we will now again apply the work and energy principle between B and then the maximum compression. So what will happen that when the spring will compress maximum through maximum displacement. So this means that the mass will stop, so the final velocity will be zero. So we can somehow visualize this problem here, that this is the final compressed position of the spring, and this was the position at location B, and this is C. So here so here x was 0, and here now we have x. So the x was maximum here, which we need to calculate, and velocity B, this was velocity B here, and velocity at C will be 0. So what we are doing here, we will apply work and energy equation between B and C. So now we need to apply the work and energy equation between B and C. So it's just the same equation, but now our position 1 is B and position 2 is C. So then what we can write is that T B plus V B plus U1 to dash or AB BC, and then TC plus VC. Okay, so now in this case, as you can see that the the kinetic energy of the body is at location B uh, is half mvb square, and at location B the gravitational potential energy and elastic potential energy is zero, because uh, the height is zero and the x is zero. So there is no elastic potential energy and there is no gravitational potential energy. And then you have this term here, which is the work done by all other forces other than gravity and spring. So in this case there is no other force, so we can also write this thing equal to zero. Now we know that at location C the velocity is zero, so this means that this term will also go to zero. And we just have this potential energy at location C, and which is again the sum of two energies, so VGC and VEC. Okay, at location C, as you can see in this case here, the height is still zero. So this means that this term mgh will be zero because h is zero. The only energy that we will have is the elastic potential energy, because the spring will get compressed. So if the spring is getting compressed, so we will have the elastic potential energy, which is half kx c square, and this xc, which is the maximum deformation in the spring, which is that we want to calculate. So if we just put the values here, so half m is 4, velocity at b that we calculated in the previous part A, which was 3.43 square, and equal to half, and k of the spring is given, which is 20 kilonewton per meter square. So this means that it is 20,000. And then the xc square, which is unknown. So from here you can calculate xc, which will become 0.0485 meter. You can say it will become 48.5 meter.